Yeah, what's up? Oh no, my live chat is missing. One sec. Where's my live chat? There it is. How's it going, guys? Good evening. It's a new day. It's a new evening. It's a new Christmas jumper. Seeing as this is what I'm calling STREAMMAS, which is STREAMMAS Christmas streaming for the whole of December. Every single evening in December, we are live streaming all sorts of shenanigans. Last night, if you missed last night's live stream, it was absolutely hilarious. We got live chat to repair an amplifier for the first time ever on YouTube, and it actually went fantastically well. Live chat successfully repaired an amplifier. Pretty crazy stuff. Yeah, what's up? What's up? Good to see so many familiar names here. If you weren't with us last night, I highly recommend just sometime where you got a couple of hours to spare, just throw that live stream on in the background and just have a watch of some of the stuff that went down in that video. It's quite funny. Really good fun, really good time. We'll probably do another one of those again at some point, where live chat repairs an amplifier. Yeah. Definitely something that we'll look to do again in the future because it was very fun. So on the live stream this evening, we're going to be looking at a amplifier that is relatively new to the market. Something that hasn't been around for ages yet. This is the B2 Riot 16K. Look at it all in its beauty. I don't know why we're getting... I didn't get this last night actually with the flickering of the camera there. Maybe I can zoom out of this camera. We can have a quick look at it in all its glory. It's a pretty big amplifier. Considering this is a full bridge amplifier, it is pretty sizable. So you're probably used to seeing, you know, the TAR amps and the Down digital amplifiers, full bridge type of amplifiers that are, you know, pretty compact for their power output. But this thing is pretty sizable for its power output. And we're going to take a look inside, see what makes her tick, see what kind of circuit design is in this. We're going to look for any things that are great about the circuit design, any things that maybe I would change, and we're also going to see what's wrong with it because this one actually is faulty. So yeah, it'd be interesting to see what's actually going on with this. Like as an amplifier that's pretty new, why doesn't it work already? Be interesting to see whether it's like a user error or something wrong with the manufacturing or something. Does it really clamp 20k? I'm not sure. I do not have the ability to clamp 20k amplifiers here in the workshop, so I can't bench it for you, but I'm sure that there's some videos on YouTube of it being benched, and yeah, if it makes 20k on the dyno, then yeah, it makes 20k. I'm not actually too sure about that. Finally made it to a live stream. Good stuff, man. Dio Carburetto. B2 prices and full bridge. Please educate me on this. Yeah, I mean, I'm pretty sure that these Riot amplifiers are very good value for the power that they are coming from B2. B2 amplifiers always have that premium quality to them. And that is true on a circuit design level. The B2 amplifiers of the past, they may share similarities in their circuit design to other brands, but they are generally always built with the highest quality components and, you know, level of build possible in terms of like everything being super thick, seated down, good quality caps, good quality FETs used, etc. Really good assembly from these amplifiers. So yeah, that's what we're doing this evening. Let's crack the back off and take a look at the guts, shall we? Kind of breaking the warranty seal here, guys. That's how new and fresh this is. Not a single mark on it. So we'll take extra care, obviously, to not put any marks of our own on it. We do that anyway, but, you know, extra care with this brand new amplifier here. Hope everyone's had a good day today. What is it? It's Monday today, I think. I lose track of the days because obviously I just work from home, so every day kind of is the same. It's not like I get a weekend or anything. Buenas noches from España. Buenos noches. Is it yours? No. This is well, it's not a custom. Well, it kind of is a custom. I imagine that this was that the amplifier was replaced. So this amplifier is very new. So I imagine that B2 replaced the amplifier for the customer, and this is now the one that was faulty that it has been sent to me to see what's wrong with. So this belongs to B2. B2 sent me this one directly. Hello, Chris. Yo. I have a very old question for you. Where do you get the most of your spare parts? So like spare amplifier parts generally from donor boards, so from amplifiers that were not worth repair. Customer didn't want to repair it because you know, it wasn't worth the repair. Then I just have a bunch of boards that were either too dead to bother spending time on, not worth the repair. Customer didn't want to have repaired. So yeah, I get a lot of spare parts from that type of board. Oh, there's the warranty sticker one, guys. Unscrewing through the sticker. So this amp has never been taken, the back has never been taken off this since it was assembled in the factory. So you're seeing this for the first time like I am. There she is, gentlemen. B2 Riot 16K. Well, well, well. What do we have here? Oh, it smells gorgeous. Oh, that new smell. When shit is new, it smells great, hey? Like lots of things when they're new smell great. This. Oh man, that's great. That is a sweet ass smell. They need to invent smell-o-vision already. Alright then. So, this obviously is a B2 amplifier, but really the circuit design resembles that mostly of a sound digital. So, in terms of power... Okay, gentlemen, I think we had a small outage there on the internet, so apologies if there was some buffering. For some reason, OBS decided to disconnect. Not done that over the last few days. Anyway, so let's take a look at this amplifier then. Now, even though we're looking at the power supply section, we need to go all the way over into the output section to start with. So most of the time, the power supply drive circuit, etc. is all going to be situated over near where the power supply FETs are. However, in these sound digital style amplifiers, because this is inherent of the sound digital design, we have to start off all the way over here in the output section, which is where the PIC is. So this is what you call the output section, but this is where the PIC lives, which is the chip that's controlling this amplifier, and it's also where we'll find the power supply drive. Ba, 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 bum, bum, bum. So, gentlemen, the PIC chip, so the chip that is responsible for controlling this chip right here, this is the PIC chip which has control over the amplifier's health check mode startup, which is something that these amplifiers have, which is fantastic, which the old Korean half bridge don't, which sucks. And this, because it has a health check startup mode, if you apply the remote to the amplifier and it detects that there are any problems in building both of the rail voltages, or building the rail voltage, or it detects DC on the output, then it will not power the amplifier up. Okay, so you never have a situation with these amplifiers where you have a damaged output section and the power supply blows itself up as a result of that damaged output section, like you do in Korean half bridge. Korean half bridge amplifiers are so outdated, guys. Let's move on. That stuff just needs to move on. And we need, you know, it's trivial to have to want to have a kind of health check mode when you've got an amplifier this big with this much voltage, this many expensive components. Why would you not test the components to some extent before letting the amplifier power up fully, which is what these amplifiers do? So the PIC chip here is responsible for the health check mode on startup. It's also responsible for listening to signals and deciding when to protect the amplifier based on thermal and based on overcurrent, and also based on high or low input voltage, and it takes that off of the rail voltage, I believe. Another thing that the PIC is responsible for, which I'm not that big of a fan of, although these chips seem to be better at it than the Tyrants ones. These PIC chips are actually what generate the PWM pulses for the power supply. So this chip has a built-in oscillator, and it generates the 0 degrees and 180 degrees phased power supply drive pulses for the FETs. So you have a little PWM coming out of here, and then it will get buffered by this chip here. This chip is the power supply MOSFET gate buffer. and it is labeled because these amplifiers, the Sound Digital started with it with scratching off the markings, which is very annoying. But when Chinese copied the design, they also decided to scratch off the markings and relabel everything. So here, this IC is called a C2. However, I believe it's a USC. Hang on a minute. I'll tell you exactly what this chip is. I think it's a UCS. Here we go. There we go. Most of the time in these amplifiers, this is what that chip is. It's a UCC 27524D. Now, that's all well and good, but you may notice that this amplifier is pretty goddamn massive. When you've been if you repair amplifiers, or if you've been watching amplifier repair, you'll notice that on older amplifiers, you'll generally have like a bank of drivers for a small selection of FETs. So each bank of MOSFETs will have its own, either its own drive IC, like a 4427, or it'll have its own drive transistors dedicated to that bank. In this amplifier, this drive IC here is responsible for driving every single power supply MOSFET on this board. Single drive IC is powering from here, all the TO220 package parts. So from here all the way to here, and on the other side. Yeah, so that single drive IC is driving all of those MOSFETs. Which actually leads us to an interesting fact about the MOSFETs that are used in this amplifier. So across the board with Sound Digital and with these Chinese full bridge boards that are pretty closely based on the Sound Digital amplifier design, because the power supply MOSFETs are all being driven by this one single drive IC, the values, the specifications of those MOSFETs must be really easy to drive. Okay, now there is a complicated way that you can calculate based on the MOSFET's gate charge value. And the MOSFET's gate charge value is how difficult is this FET to charge, and the input capacitance is also related to how difficult it is to charge. But generally, when you're looking at a MOSFET and you're looking at, right, is this MOSFET going to work in this circuit? One of the most important things about seeing whether that MOSFET is going to be driven okay is looking at the gate charge value of the MOSFET. And you can check that by looking at a datasheet for said MOSFET. So let's take a look, and let's have a look at one of the common MOSFETs which are used in these amplifiers. So this is the factory stock MOSFET which is used in these amplifiers. Okay, and this is a CSD 18502 KCS, 1852502 KCS. This is what's used in these amplifiers on the power supply section. So we see here that we have a drain to source voltage of 40 volts, which is that's absolutely fine. The power supply section is obviously running on like 12, 14, 16 volts, and when it's given to a transformer, it rises to about 24 volts or something like that at its peak. Absolutely fine. That's well within limits. And then let's have a look down here now. Total gate charge. This is important. Gate charge total. This is with 10 volts worth of drive on the gate. So when the gate has 10 volts on it, the total gate charge, the amount of charge required to turn that FET on, is 52. Can't remember what that unit stands for. Nano something? Nano charges? Maybe someone in the live chat will tell me. I can't remember. But essentially, this value is really, really freaking low, which we'll see in a minute. This MOSFET is capable of syncing 100 amps, which is the package limit. So this MOSFET, Okay, this will be available in various different sizes usually. I've chosen the KCS variant, which is in the TO220 package. Now, the actual silicon part of the MOSFET might have a higher current handling rating than the package that it's in. So you'll find often with different MOSFETs, you'll have the same MOSFET number, but it will come in a variety of package options. You might see it in a surface mount option, TO220, you might even see it in a 247 AC, but usually it's a slightly different model number. But essentially it's the same silicon die, and it will be installed into various different packages for different uses. Now, packages will often have the current limits of their own, because when you look at this MOSFET here, we have the 3 legs that go up into the MOSFET here, but then there needs to be some small little leads of wire that connect these legs up to the silicon. And additionally, we also, these legs themselves of the MOSFET, these are like fuses. So, you know, if you draw too much power through any of these legs, they're going to blow open just like a fuse will. So not only do you have the limit of the silicon die inside this MOSFET, you also need to take into consideration the limitation of this package, TO220. So what this tells us that the continuous drain current, so if you're drawing continuous current, not switched, not pulsed, this is continuously drain, like DC, the MOSFET is continuously on. If you're drawing current across the silicon die or across this MOSFET, the limit of the package, the limit of the TO220 package here is 100 amps continuous. However, if you keep the silicon die at 25 degrees Celsius, you can draw as much as 212 amps from that silicon die before the silicon fails. Now, obviously, the package here is going to fail before the silicon in this instant. However, remember, this is continuous drain current, and when we are running these MOSFETs in a switching power supply, we are not running continuous current through it. We are pulsing the MOSFET on and off. There's another rating here which gives you pulsed drain current. Now, this value here, 400 amps, this is based on a single pulse. You see there's a little 1 here. If we click on the 1, it usually tells us does it usually... here we go. No. Here we go. Yeah. Absolute maximum rating. So this pulse drain current is... I can't remember exactly what that bit means. But basically, the pulse duration is less than 100 microseconds. Duty cycle is less than 1%. So that is not a 50% duty cycle pulse. That is not continuous pulsing like we see in the car amplifier power supplies. That is a singular tiny pulse spike. So this MOSFET can spike 400 amps for a literal fraction of a second here. But what we can do here is, although this doesn't tell us the exact amount of current this MOSFET can pass in our conditions, but we use these values and we can use this to make a get an idea as to how good this MOSFET is going to be in our situation, in our application with this amplifier. So these values are all pretty important, but I would say that the most important ones are going to probably be the silicon, like the ones to look out for. Obviously, the package limit is going to be the same, because regardless of what MOSFET you look at, it's going to be about 100 to 130 amps of continuous drain current on the package. But we don't want to look at the silicon limited current drain. We want to also just take a quick peek and see how quickly that drops off with heat. Now, remember, MOSFETs will lose their ability to pass current as they heat up, as the resistance gets higher across the silicon die. So some MOSFETs drop a huge ball-ass bit of, they drop massively between 25 degrees Celsius and 100 degrees Celsius. But this one here drops from 212 to 150 when it reaches 100 degrees Celsius, which you should never really have, but that could happen. When your amp is cooking up hot and it's too hot to touch, the case might be, I don't know, 65, 70 degrees Celsius, but the MOSFET could be close up to 100, so you need to bear that in mind. We also can take a look at the Draced Pone current, pulse drain current. Now, obviously, we're not going to get 400 amps from it because our duty cycle is up at near 50%, and the pulse duration is much slower. But we can use that as to give a rough idea as how this is going to behave when it's pulsed, when it's switching. So, this MOSFET here, I can tell you, is a pretty powerful MOSFET. But what makes this MOSFET so insane is the fact that it is as powerful as it is while having such a stupidly, ridiculously low gate charge total of 52 NC. Not only that, but we also have an additionally ridiculously low input capacitance value. See, that is really low. By comparison, let's have a look at some other MOSFETs that are used in other amplifiers. So let's look at the IRF 14. 1404. Let me just check the live chat, make sure everything's working. Yeah, everything seems to be working good still. Just making sure I wasn't disconnected or something. Let's have a look at the IRF 1404 real quick, and let's compare that. So these MOSFETs are generally what you'll find in tar amps, especially in the HD series, like the older HD 5K, HD 8K, HD 10K. These ones are what you'll find in those in the TO220 package. So in these ones, we have a 1404 PBF. We have... Let's take a look at these values again. So we have... don't think it tells us the package limit. No, it doesn't tell us a package limit, so all of these are silicon limited values. So we have 202 amps of continuous drain current at 10 volts at 25 degrees Celsius, which is almost the same as our CSDs that we're using in this B2 amplifier. Where's that gone? That is down here. Nope. Up here, maybe? Yeah, here we go. So it's almost the same. It's 10 amps less, in fact. The continuous drain current at 100 degrees, again, it's about 10 amps less. The pulse drain current, however, is over double, which means that this FET will perform probably slightly, even though the continuous is slightly lower, we can pulse quite a lot more, which means that the FET will heat up less as it's being pulsed, even with a higher duty cycle, I would imagine. And total power dissipation is important to look for as well. This is how much heat the MOSFET can dissipate. Does it tell us on the CSD one? Yes, 259 versus 333. So the 1404 can dissipate a little bit more energy as heat to the heatsink. However, so these MOSFETs are roughly, they're pretty similar, right, in value. These MOSFETs are pretty similar in their specification, in their ratings for power, etc. However, take a look at the ratings for the gate charge and the input capacitance of this FET. The gate charge, okay, is almost 3 times as high on the 1404. Now, the input capacitance is higher, but not too bad. But this is 3 times higher. So essentially, if we swapped out these CSD FETs in the B2 for 1404s, then this little driver, I don't know if it works exactly linear with like 3 times the amount of gate charge, 3 times the amount of stress, but basically that's going to stress this little drive IC that's powering all of those FETs quite considerably more than if we just use the original CSD FETs, because that is almost 3 times as high amount of gate charge. So it's going to need 3 times the amount of charge to turn on all the FETs. Additionally, let's look at another MOSFET here, the one last one, IRF B3077. This is a fantastic MOSFET that is used in Banda Viking amplifiers, like the Viking, is using the Viking 7K, Viking 8K, and I think it's used in the 10K as well. So this one right here has a continuous drain current, silicon limited, very similar again, very similar specifications, very similar pulse drain current to the 1404, maximum power dissipation, very similar. However, let's take a look at these values. Input capacitance, 9,400 picofarads. That is like double the CSD. And total gate charge, again, is like about 3 times as high. So when it comes to repairing, these Sound Digital and these B2 boards, it's important to consider whether you can drop in different MOSFETs into the power supply section, because we need to take a look at the drive circuit and have a look, okay, how strong is that drive circuit? Is it actually going to be strong enough to drive these new FETs I'm putting in? What is the specs of these new FETs I'm putting in? And you know, it's important to check that out. So I personally haven't tried putting in 1404s or 3077s into these Sound Digital boards before. I've got one that I'm working on at the moment, which I have ordered some different MOSFETs for, because the CSD ones are very difficult to get in the UK. Oh, Matthew, thank you. I sorted that out. But yeah, this one here is interesting because, like I say, they have specifically used these MOSFETs because they are low gate charge and for this single power supply drive IC. I imagine that, originally that decision for this circuit design might have been to save costs. I mean, these MOSFET drivers, they're not expensive, but they're not like crazy cheap either. And when you're looking at manufacturing, every tiny little saving you can make in cost is very important. So if you have available to you a MOSFET that is more than powerful enough, but that has a really, really low gate charge, which means you can get away with just using a single drive IC for all of the MOSFETs, then why would you not do that? That would make sense in terms of cost saving. You need less drivers. You know, it's an easier decision to make. So that's about the drive circuit of this B2 amplifier. Yes, I've seen some Brazilian amplifiers go down too. 0.5 ohms, Tyrants do, especially base model amps. All the bass line will do 0.5 all day. Although the MD line does, they have the option of 0.5 or 1. Tyrants has definitely got better. The original HD line of amplifiers had a massive problem with the power supply section. There was a design flaw in there somewhere. It was so terribly unreliable. More than it needed to be. Like when you compare the Tyrants 10K to the Band of Viking 8K, the boards were very, very similar. The circuit designs were very similar, using the same drivers, the same output section, the same MOSFETs, everything was the same. But for some reason, the band amplifiers never killed their power supplies. It was only the output FETs that would ever die. But the Tyrants, you'd see more of those with random dead power supplies, but the output section was okay. So the power supplies just killed itself. You saw more of that with the Tyrants. So there was definitely an issue there with the design. I said for a long time, actually, that if you were to cut a Tyrants and a Banda in half and put the Banda power supply section on the Tyrants output section, you'd have a great amplifier. Because each one seemed to kill the other half of it. So if you took the two good halves and put them together, it'd probably work great. So we looked at the drive circuit of this amplifier now. We looked at the PIC, which generates the pulses, passes it onto this drive IC, onto the MOSFETs. We talked about the MOSFETs in the power supply section. Now, as you may have guessed, because this is originating from like the sound digital kind of design, and it is made in China now. I think these are the Chinese ones, I believe. This design was definitely copied by the Chinese. We don't have any markings on the power supply FETs. So if we take a screw off here, and we take a peek, I think it's going to be remarked. Yep, there we go. So that MOSFET there has been remarked with H1, which is the CSD MOSFET, which I showed you a moment ago, being this one here. So that is the H1. And it's quite important, for reasons that I just explained, why you make sure you stick with the same original MOSFET if you can. Otherwise, be prepared to do some trial and error with buying a bunch of replacement MOSFETs and seeing whether they work or not. Okay, so that's the power supply section in terms of the FETs and drive. Now, the transformers which are used here are these totally encapsulated ones, which are, they're not, I can't remember the correct name for this type. It's not toroidal. My words are terrible this evening. But this type of transformer is used here, which, like you say, you'll recognize from sound digital style boards. And from the people that I have spoken to who are much more better informed about transformer design than I am, I'm led to believe, and I have been told, that the more kind of the typical style transformer that you see in car audio amplifiers, this style of transformer, is actually better. This one is the better style of transformer to use than this one. However, these ones are able to be a lot more compact, which is number one, and number two, these transformers do not suffer from vibration damage like the more typical car audio transformer do. So, you know, if you're looking at weighing up the positives and negatives, if these ones perhaps aren't quite as good in terms of their amount of power they can pass for their size, for example, but you get the benefit of being able to fit more of them into a board, into a small area here, and you also get the added benefit that they don't suffer from vibration damage. Well, you know, maybe you just add a few extra than you would have done otherwise with the other style transformers, and reap those benefits of having them compact, easy to solder in, because they're all like, you know, they're already in their little cases here. So actually soldering these in the factory is way easier than the other ones. And also they don't suffer from vibration damage like the other ones do. So that's not a bad call actually in my book. That's absolutely fine to see, provided that there are enough of them to do the power that the amplifier is going to demand. On to the output section then. Let's take a look over here. What do we have here? We have some fans in here, which you'll notice. Now these fans, there is a hole in the board at the bottom there. So what these fans are going to do is they are actually sucking air in from this side. So air is going to come in from the these vents in the heatsink here. So you've got some vents on the sides and at the top there, at the bottom. And you've got also some fans here. And this is slightly strange because of the fan orientation. So on this side, you've got open vents, okay? On this side, you've got fans that are blowing air out of the PCB, okay? So that's taking heat from the transformers and the power supply MOSFETs. It's taking it out of here, okay? Also, the heatsink is kind of ribbed. It's ribbed and it's grooved all along the edges, which will increase the surface area, which is good for heat dissipation with these fans. I would like to see these MOSFET clamps with some fins on them. That's something that you actually see in a lot of older amplifiers, like Hyphonics actually, for example. Some of the more premium Hyphonics amplifiers from a long time ago actually had really quite significantly finned MOSFET clamps, which do help over, you know, a long booming session, especially if you've got active air cooling with these fans blowing air over them. So that's going to be taking the air out of the power supply side. Now with the output section side, you've got these fans here, which are sucking air down in like this. And that's probably going to get its air source from this side of the board as well, which is the same as where these fans get their air source. So air is going to be quite drastically pulled in from here. Then some of it is going to go down into these fans. And then some of it is going to come down the heatsink, past the power supply MOSFETs, past the transformers, and out of the board, which is not too bad a airflow design. I maybe would have... That's the thing, it's a trade-off between noise and airflow, right? I maybe would have added some additional fans over this side to just improve the air getting into the board in the first place, because we've got, in this instance, we've actually got a negative air pressure, negative pressure environment, because we've got active cooling fans blowing out, and then so we'll have a negative pressure environment inside the amplifier. I think I prefer positive pressure environments, because with air pressure, okay, the more pressurized the air is, the more air particles there are to extract heat from the components inside. So I probably prefer a positive pressure environment, but you know, this is a very niggly. It's not going to make a huge difference over in the grand scheme of things, but it's just something that I would like to point out. And then the air gets pushed down here, through here, and it's going to be pushed right up against the back of this plate here, which is also grooved in the back, and it's going to come out here. So we've got a groove slot here, so air is going to be coming out of here, and also I think it's probably going to be air coming. Is there another one over here? Yeah, air out of here. So what you'll do is you'll have hot air from the output section coming out of this groove at the top here, and this groove at the top here, and you'll have cold air being sucked in through this vent, and you'll have hot air from the power supply being blown out of this side. That's the cooling solution. Rail capacitors, we have a whole bunch of rail capacitors. Now this is quite a considerable number of capacitors for a Brazilian amplifier. However, for a 20,000 watt amplifier, it's not as many as other brands, non full bridge, non-Brazilian design amplifiers. Now, one thing you'll find about amplified circuit designs that originated in Brazil is that there are less rail capacitors than normal, and you can actually see the effects of that when you watch amplified dyno videos. So in your spare time, at some point, if you're interested, have a look at some amplified dyno videos where they measure dynamic power versus the certified power. So, you know, most dyno videos, they'll go certified, uncertified, dynamic, okay? And most people don't really care about the dynamic power, but it's important in this instance. Let's say you have an amplifier that's doing 3000 watt RMS certified. This is like a, let's take an old Korean half bridge that's got a shitload of rail caps. It's like proper beefed up inside, massive guts inside. It makes 3000 watts at 1 ohm on the amp dyno certified. Then with the dynamic power, it's able to create like 5.5K. So on the dynamic burst, you see 5.5K. And the reason for that is because you have so much energy in the rail capacitors that on that small dynamic burst of power, the clip point is actually way higher than it is normally when you're running the amplifier continuously. So what happens in the amplifier when you draw current, when you play a bass tone and you draw current from the amplifier, okay, let's say that the rail capacitors, let's say that your rails for the output section are up here like plus 100 volts, minus 100 volts, and the amplifier is sitting idle. when you play a tone into the amp dyno or a subwoofer and current is drawn from the amplifier, your rails are no longer 100 volts plus minus. Because of voltage drop across the components inside, especially the power supply, your rails sink down. They droop like this to about maybe 88 volts plus minus. So your clip point is now at 88 volts plus minus. And as soon as you turn the tone off, the rail voltages go back to plus minus 100 volts. So obviously your RMS power at clipping point is limited by the rail voltages, which have now sunken down to 88 volts. However, that 100 volts plus minus, there's a lot of this energy is stored in the rail capacitors here. Okay, so on an amplifier that has lots and lots and lots of rail capacitors, when you do a tiny burst, like a dynamic burst, like a kick drum, for example, in your music, or a dynamic burst on the amp dyno, basically the sine wave goes up to this plus minus 100 volts rails, and because that the voltage drop that causes this to sag down happens in the power supply section, not necessarily so much the output section, you get a burst of sine wave that actually doesn't clip at 88 volts. It actually, its clipping point is all the way up at 100 volts plus minus, because that is the capacitors are able to instantaneously supply that power for that burst before the voltage droops down due to the voltage drop due to the resistances in the power supply section. Yeah, so the more rail capacitors that you have, the more dynamic power you're going to get from your amplifier, because you're able to run your sine wave up to the point where it usually is before a signal is played for that initial burst. With an amplifier that has less numbers of power supply capacitors, when you do your dynamic burst, those capacitors are, because there's less of them, they're going to deplete far quicker. So your dynamic burst on a Brazilian designed board is the rails are gonna be like boom, boom, boom. So that's limiting your dynamic power to similar, more like where your certified power is. If you look at the amp dynos of Brazilian amplifiers, you notice that it might make 5,000 watts certified and maybe 5,100 or 5,500 watts dynamic. It's not that much different, but on an older Korean style amplifier that has massive loads of rail capacitors, the difference in dynamic power is quite considerable because you have much more energy stored in the rail capacitors there before the voltage drops down. So yeah, Brazilian dynamic power, the rails might go doo, doo, doo. Whereas on a Korean, it might go doo, doo, doo. Like this, like only move a tiny little bit because there's more energy stored in the rail capacitors that is instantaneously available to the output MOSFETs. They haven't got to get it, they haven't got to fetch it from the power supply section, it's instantly there in the rail capacitors. So for a 16K amplifier, this has sufficient rail capacitors in it to make its rated power absolutely fine, and one of the main reasons for the rail capacitors is also to clean up and smooth any rippling from the power supply section's rectification diodes. So they're absolutely more than sufficient to do that. This is just this is a fair number of capacitors, but it won't quite have that dynamic power that it would if it had the scaled same number of capacitors that older amplifiers would have had. You know, if say for example, go back sort of 10 years or whatever, let's say that DC Audio released a DC Audio 20K, which was based on the same circuit design as their 10K. That thing will have had probably, I don't know, 20, 30 rail capacitors in it or something, and it would have, the dynamic power that thing would have been capable of would have been quite monstrous compared to what this will be capable of. But at the end of the day, when you're playing tones and stuff like that, you're not using too much of that dynamic power anyway, so it's not a major problem. It's not something that's going to have a massive impact on your system, or it's not going to prevent you from being able to hit dBs. It's not going to prevent you from being able to listen to certain types of music. It's just something that is different about these amplifiers in how they work, and also in their dynamic power readings on the amp dyno. Cool, so that's the rail capacitors. Now let's move on to the output section itself. Let's shimmy this over here. So the output section itself starts, let me see, where are the rectifiers? Are these marked S, S5, S6? I think the output MOSFETs start here. Let's have a quick look. D1. Yeah, okay, cool. So the output section officially starts, where are we? Here. So from this point onwards to this point, between my hands right now is the part of the board which actually is creating the 16,000 watts RMS. This is the amplifier. Everything before my hand here is just converting 12 volts DC into high enough voltage for the amplifier to use. But you know, if your car was capable of giving high voltage DC to the amplifier, then it would only need to be this big and it would be the same amount of power. So the output MOSFETs here, of course, because this is coming from one of those factories that rubs off the markings, we have the output MOSFET, let me zoom in a bit, is marked as a D1, which means nothing to us unless we had the documentation from the build house on what these are. But here we go, D1. Now, generally in these amplifiers, the MOSFETs which they're using in the output section are going to be the highest current available, or the highest power available in the rail voltage limits of this amplifier. So yeah, for example, let's say that you know, we needed a 200 volt MOSFET in a TO in a 247 AC package. We'd probably be looking at something like a 90N20D, which is one of the most powerful 200 volt MOSFETs in that package. That's, you know, actually affordable. So even if you don't know what the output MOSFET is, if you look online and you have a look at what the most powerful FETs are, and usually they're using international rectifier. So look at international rectifier parts, IRF parts, IRFB, IRFP, etc. And look at your rail voltages. Choose the MOSFET which is a little higher than what your rail voltage limit is, with maximum input voltage to the amplifier, and then you choose the one that has the most output current and the lowest RDS, and that's probably the one that they're using. That's why Triumph's 100 volt amps are so small, right? Yeah, exactly. So many of the Brazilian brands, they offer high voltage amplifiers, which are amplifiers that you don't connect to a 12 volt battery. You connect to maybe 200 volts DC or 100 volts DC by linking up car batteries in series. And yeah, the reason that they're so small is because you can just cut off this whole part of the board. You don't need it. You only need the output section because you're already giving it the required voltage to make that power. So that's why they're so small. Sam, there's a ghost behind you. He's learning amplifier repair. What? Don't say that. There's a ghost, upper right corner. Wait, upper right. Is that one? Don't scare me like that, man. I had to set some 5cam that just stopped working, and if you hit it at the top, it would start working and kept doing that. That's vibration damage for you, my friend. Remove your amplifier from your sub box, or take it off of whatever is vibrating. That's why it's dead. My lighting. Yeah, I see it. Yeah, actually, I see it. I see the nose. Yeah, okay, cool. So that's the output MOSFETs generally, yeah, they'll be the highest rated ones that you can find from international rectifier in most cases. So we're gonna sort of take a good guess as to what these ones are, because I can't remember what these D1s are off the top of my head right now. So we're gonna look at that together. Now, in terms of the output drive circuit, let's have a look, see what we have here. We have here are the drive ICs. So these ICs are what's driving the output MOSFETs. These are labeled with a C5. However, I believe, I can't remember. I think these ones could be either IRS 2092S or the Silicon Instruments ones, which are SI2 something. I'm pretty sure that these could be 2092s, but we'll double check that. Actually, I have a video on this. I could just reference my own video. I did this in a stream the other day when I was working on the sound digital. Like, I can't remember, because I don't write things down, right? So I made a video on how to repair sound digital amplifiers, and I went through exactly what the parts were. So I could just go back and look at that video and find out, because I can't remember. So these are the output drivers, but these output drivers are also buffered by tiny little buffer chips here and here. So these take in the input signal. They then create a high-low side sort of self-oscillating environment for the MOSFETs to oscillate at 50% dead time. Watch my video about how Class D works to understand what they're doing and why they do that. And then they pass this drive on to these little tiny drive chips here before going finally to the MOSFETs. It's a very simple drive circuit. You can see here that this tiny little bit of circuit here, this little square, this is just the output drive circuit for one side of the full bridge, and this little square here is the drive circuit for the other side of the full bridge. This little bit here is the power supply drive, this bit here is the PIC, the brains of the amplifier controlling it, and this bit here is the preamplifier circuit. So yeah, all very small, very simple. I'm not that impressed with the quality of assembly on the potentiometers here. Look how skew whiff they all are. You got like this one's pointing in that direction, this one's like kind of on that angle, and they're all angled kind of strange. And when you look at it through the end of the amplifier here, through the side, they don't actually line up with the holes exactly right. Like the gain knob is actually way off to the gain is way off to one side. So I can show you that. Yeah, look how far the gain off is way off to one side. So, you know, just it's fine. It's not going to affect the operation. But in terms of quality control, I'd want that to be a bit more central than it is. Okay, cool. So that's a general overview of the amplifier. It is pretty much the same as the Sound Digital original circuit, but this is the Chinese kind of copy of it. And it is the same kind of stuff as what you'll find in Ground Zero. Ground Zero are also using this build house, and they offer amplifiers like 8,000 watt, I think there's a 12K. But yeah, it's the same board, just scaled up in size. And for the value for money, it is very good. Like, this is a lot of power for your money. So you know, you can't really go wrong. There's a lot about this amplifier board that, like I've said, I like the way that they've done quite a lot of things in here. There are some things that I would do differently. Like, for example, I wouldn't use a single drive chip to drive all of the power supply MOSFETs. I would probably use some slightly different, more available MOSFETs, and drive them individually like they do on the banders and stuff like that, and the tar amps and stuff like that. The output section, yeah, it's fine. I would probably add a bit more filtering. Now, this actually does have slightly better filtering than a lot of the tar amps and stuff used to have. We have obviously the output filter inductor here, and then we also have some pretty big film capacitors here, which are also going to be soaking up any really nasty big spikes that happen, especially at clipping point. Actually, you know what though? One thing that I will say, which isn't too much of a problem, because luckily this board is very thick, okay? But look, the amplifier, the board is actually designed with having central screws in mind. So you see here, this is a plastic clip kind of bit for a central board screw to screw down into the heatsink to, you know, help prevent vibration damage, help the board stop flexing if it's mounted to a sub box in a vehicle installation. So we have another one there as well, but obviously there's no screws in it, and the reason there's no screws in it is because there's no thread in the heatsink the other side. So they've put these plastic clips in place, which are, I guess, kind of like little, they're little pillars. They do help because they're pushing against the heatsink there, but there's no screw in it, so there's nothing actually preventing the board from flexing upwards. Like, it won't flex down because that's in the way, but it will flex upwards a little bit, albeit not very much. So I imagine that they maybe decided that it was unnecessary, because it seems pretty solid to me anyway. Like, this is not a very bouncy board, so out of all the boards that you see, this is not going to be one of the ones that generally I would say suffers from vibration damage in that sense. Output inductors, in terms of how well they're seated, yeah, not too bad. There's a fair bit of movement in that. If this was mounted to a really badly designed box, and if this was flexing a lot, this could cause issues in the future. I don't know whether there is anything underneath this. So you see this silicon here. I'm not sure if there's anything underneath these inductors between the inductor wines and the board. It doesn't look like there is actually. It looks like the inductors are just sitting on the PCB with nothing in between. So if that rubbed enough, that could rub through and it could short to the board if there was a trace there that, you know, it shouldn't be shorting to. It doesn't look like there is any big traces underneath the inductors, but if there was, it could potentially pose a problem. Yeah. So the reason I've got this amplifier is because this amplifier does have a problem. I don't know what that problem is yet. What I've been told is that the amplifier, it doesn't have any sound, and when you try and power it up, you have the, I think is it the power and protect lights constantly on, or is it the protect and clip lights? Just power and clip. Okay, so when this amplifier attempts to power up, we just have power and clip lights. So let's plug it in, and let's see if that's what we have, and let's see why, and see if we can fix it. Plug our power leads in here. Bevids, how come when you change to one of your close-up cams, your mic gets noticeably louder? I don't know. I was trying to figure this out the other night. I don't understand why that happens, because obviously I'm using OBS, Open Broadcast Software, right? So this is my OBS screen, okay? Now, you can see here my mic levels, on here. Now, when I switch to a different scene, unfortunately, because I'm switching to a different scene, you obviously can't see that because now I'm coming off of this screen capture screen. But the mic level doesn't change. So guys, tell me which scene it gets louder on. Okay, I'm gonna start with this one. Okay, so this is screen number 1. So if I go down to screen number 2, tell me if it gets louder or quieter. Okay, so that's from 1 to 2. Is there any difference? From 2 to 3, any difference from 2 to 3? From 3 to 4, any difference there? I can't figure out exactly why it's doing that. Screen 2 is louder. What the why is this screen louder? Very strange. So on this screen I have, let's just show you what I have on this screen. I want to get this just figured out real quick. So I'm just going to show you what I can see on this screen here, right? So here, this is the RTA mic for this screen, which is also the same as the RTA mic on this screen, and the actual level is the same. It's the same level regardless of what I do, and there's no other microphones on here. There's no other microphones on here that are contributing to the sound. If I turn the JVC on, that's probably quite loud, so it's not that. Filters maybe? Gain? No. Gain's not. The gain is off. There's no gain applied. Yep, I don't know, guys. No idea why that is. PS cam. Desktop audio. Yep, no idea. Guess the only way to fix that would just be to like reset my OBS and see if it makes a difference. Anyway, let's continue with powering this up. Are you sure the sliders are the same on? That's a good point. Let's just quickly check the sliders are the same. So between here, the slider is at 0 dBs. And on this one, the slider is also at 0 dBs. Yes. It's like at full on both of these. So not too sure what that is. Get rid of display capture. Let's fire her up then, baby. Let's give her some power and see what's happening. So first thing I'm going to do then is I am going to probe the power supply MOSFET drain. That's an important one. Now remember how I said at the start of this stream, these amplifiers run through a health check mode when they power up. It's really annoying actually, this camera angle doesn't let you guys really see inside the board because of the angle. Let me see if I've got something I can just like prop the board up with here. Maybe a screwdriver, maybe these pliers. We'll just prop this up slightly just to give you a bit of a better view. There we go, that's one. Other side. Okay, that's a little bit better. So power supply MOSFETs, yep, all along here. So what we're going to do, when this amplifier powers up, it enters into a health check mode. And what it does for the health check mode is it sends a few very, very tiny pulses to the power supply MOSFETs. And what that does is it builds like maybe 5 to 10 volts of rail voltage on the output section. Then once it's built a little bit of rail voltage in the output section, it detects where that rail voltage is, and it detects the rail voltage limit. It detects how much rail voltage is built. So this amplifier is designed in a way that it turns on first with a few small pulses. It then checks, did those small pulses build enough rail voltage for this amplifier to be okay? Remember, if there's a problem in the output section, it's most likely that output MOSFETs are shorted. And when output MOSFETs are shorted, they won't, the rail voltage that is built will just be straight grounded. So the rail voltage won't be sticking around in the output section, it will just go straight to ground. So if there's a short circuit in the output section, no rail voltage will be present. The PIC chip will detect that and it will say, hey, I just sent some pulses to the FETs and I got no rail voltage. I'm going to go into protection mode because that's not right. So what it does, if it detects that there are enough rail voltages there, then it will then continue to power up fully into full operation. Then hopefully it doesn't explode. Just real quickly, because I've been talking for a long time, I probably missed some donations here. So I want to say a massive thanks to Matthew McKeever for the £2. Are toroidal transformers better for hi-fi amps? I don't know enough about transformers. Transformers is a slightly weak area for me. I do have a guy who would know the most about that. But I think that toroidal transformers are generally better for high power applications across the board. I think for their size and everything, they are able to pass more power than the older style. Tom, thank you very much for the $10, my man. Thanks for sharing your mind and experience and time with us all. Good job. Thank you very much, dude. Massively appreciate the 10 there. Awesome. Thank you, dude. And thank you again also to Rob for the 10. Love watching your videos. Have learned a lot. Awesome. I'm really glad you've learned a lot, buddy. That's the key point of this, is to educate and get people interested and excited about repairing stuff. So now that you know how the health check mode works, let's put our power supply, let's put our probe on the power supply drain, which is leg number 2. Just here, and let's see what we have on the scope screen when we turn the amplifier on with the remote. Ready? So we should see, turn my scope to the right settings, we should see a couple of tiny little pulses from this power supply MOSFET. Helps if I turn the power supply on, doesn't it? 12 volts. Let 4 amps pass. Okay, interesting. We're actually drawing quite a lot of current already. Despite... No, it draws a lot of current right away. Now, this might be a slightly different... because obviously this PIC chip, you can program it to do whatever you like. Now, with tar amps, Banda, and sound digital amplifiers, the PIC is programmed to do tiny pulses, and then if there's a problem, it will shut the amplifier down and won't turn on fully. This PIC from the Chinese factory may have been programmed slightly differently to do either a larger pulse or just do a much more intensive kind of power up procedure where it does a much larger pulse. So yeah, as we can see on the scope screen, the pulse that it sends there is pretty big, to be honest. And it's drawing all of the 8 amps that I am allowing into the amplifier on that initial remote burst. So obviously we've bursted quite a bit of a few pulses into the amplifier now. So provided there are no shorts in the output section, we should see some rail voltage being built on the output FETs. So let's take a look at the output FETs over this side of the board. We want to see if we have rail voltage on the output FETs. Okay, we don't actually. Oh, there's a bit of voltage there. Okay, yeah, maybe high and low side. Okay, so we've got 22 volts worth of rail, and if I pulse the remote a little bit more, you see that slowly start to rise? Yeah, so okay, the positive rail is building. Now, I think these amplifiers are single-ended, which means that they only have positive rail. There is no negative rail voltage in these amplifiers. So it would appear then... Ah, that's different, I think. Hang on. Ah, that's different. Okay, I think I have seen what the problem might be here. So these amplifiers, what they will do, the way that they work, is that because we only have a single positive rail voltage, there's no negative rail voltage, there needs to be, the amplifier needs to think that there's a negative rail in order for this to work, in order for the sine wave to swing between plus and minus, top and bottom. So what this amplifier will do is instead of having negative rail, ground, positive rail, instead you'll have ground, middle, and positive rail. So these amplifiers will kind of generate a floating ground point on the output section that is about half rail voltage, and it treats that as the sine wave's 0 volts. So the sine wave will then swing down to ground and up to positive rail, down to ground, up to positive rail, from this kind of generated midpoint in between the positive rail, half of the positive rail. So what we need to see on this amplifier is on the what is it? The low, on the, remember this right, on the high side. That's right. On the high side MOSFET, we need to. So usually, like if you're used to seeing me work on half bridge amplifiers, on the high side MOSFET, we usually have 0 volts gate, positive rail drain, 0 volts source. Okay, so 0, positive, 0. So in this amplifier, when we probe the high side FET, we actually get, let's bring this over to the, can I show you the high side FET real quick? The angle is terrible. Go over here. The high side FET, okay, instead of having 0 volts, one sec, plug my power lead back in. Instead of having 0 volts, positive rail, 0 volts, we actually get, on the gate we get 10 volts, on the drain, we get 29 volts, so it's not quite halfway yet because the amp's not powered up fully. And on the source, we get 10 volts. So the high side, we have like lowest voltage, positive rail, lowest voltage. On the low side, okay, we have 0 volts on the gate and 0 volts on the source. Yeah? Usually on the gate and source, we have negative rail on a half bridge amplifier, but in this case, we have 0 volts because this amplifier is treating 0 volts or ground as its negative rail. So yes, so although we have 0 volts on gate and source, that is essentially negative rail as far as this amplifier is concerned. So on the low side, we have 0 volts on gates and source, leg 1 and 3, and on number 2, on the drain of the low side, where we would usually in a half bridge amplifier have 0 volts. So a half bridge amplifier low side would have negative rail, 0 volts, negative rail. In this amplifier, we have 0 volts on the gate, which is treated as negative rail. On the drain, where we would usually have 0 volts, we actually have what this amplifier is treating as 0 volts. We have the 10 volts. Yeah, so that kind of half generated rail. And then obviously on the source, we have 0. So this all looks correct for this half of the amplifier. So this side of the amplifier has those things. On the high side, we have half rail, full rail, half rail, and on the low side we have 0, half rail, 0. Now the other side should be absolutely identical. So on the low side we have 0, 0, 0, and on the high side we have 0, full rail, 0. So that possibly suggests to me that we might have a shorted low side FET on this side of the amplifier, because we are not getting that generated, that sort of like half rail generated voltage on this side of the amplifier. So let's take our multimeter let's have a look and let's see if any of the output FETs are shorted here. What we're going to do is take my pull down resistors and just get rid of any voltage that is still floating around inside the amplifier here. That should have got rid of any residual rail voltage. Nope, it didn't. Where's the rail voltage on these ones? Oh, I was probing the wrong thing. Rail voltage is pin number 2 of that. Because I don't want to be probing around when there's 26 volts of rail still in there. Okay, that's got rid of the 26 volts of rail. Just confirm. Yep, that's all gone. Okay, so let's now check for resistance across the output low side FETs. You know what I'm going to do? I'm going to bring this camera over a bit to give you a better view of what I'm doing inside the amplifier, because the cameras aren't so great this evening with seeing inside this amplifier. So let's go over to here. There we go. That's a bit better, isn't it? Okay, so these are the FETs which I imagine might have a short on them. Ah, well, would you look at that? We have a short circuit across all 3 legs of this low side bank. Okay, interesting. Well, Jesus, every single leg is shorted of every single FET on the low side here. Yeah, every single FET, every single leg is a dead short. Not even like a small bit of resistance. It's a dead short. Well, that, you know, this one's now 12 ohms. Okay, have a look on the multimeter here. Yeah. Actually, that's pretty cool. I can do that so you can see the multimeter in that screen. That's pretty cool. I like that. So, first MOSFET. Between gate and source, we have 1 ohm. Second MOSFET. Between gate and source, we have 0. Third MOSFET, gate and source, we have 12 ohms. Which, actually, this MOSFET could be okay. We could just be reading the gate resistor. This one, we have 1 ohms. This one, we have 19 ohms. So that MOSFET could be okay. We could just be reading gate resistor. And this one we have 0 ohms. Okay. So let's remove the screws from these ones. Hertz to 25 hertz to live says you're missing wine. Go get it. This evening I'm not going to be drinking any wine because this is a like a customer, or this is a business repair. So I'm looking at this amplifier in a professional manner for the owner of B2 Audio. So it wouldn't be so it wouldn't be so respectful of me to be downing wine while I'm doing it. Just want to stay on top form. I can down wine when I'm looking at my own amplifiers, or like that janky thing from last night, because that doesn't matter. But yeah, this evening, nah, we're not going to be drinking while we're working on this amplifier here. So yeah, okay, there we go. There's all the low side FETs then. D1s. So yeah, I can just snap these off because it's quite clear that these have encountered a problem, and it's probably the best thing to do is probably just to snap these off. Now, you might remember from my stream the other night that my soldering iron broke, and I'm just waiting on the parts for that. So we can't actually desolder these just yet. But I think, yeah, we can probably just get away with snapping these off, removing them from the circuit, and might be able to see if there's any survivors, and use the survivors to confirm the integrity of the drive circuit here. So the low side is, what are we consisting of? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we've got 6 low side FETs, 6 high side FETs. Randall says, oh, Sam, I have the same problem with my 16K. Same side, blue, 2 FETs. Interesting. I wonder if there is something funky with these then. Okay, I'm going to snap off these first two because these definitely have a direct short across gate and source. So let's get rid of these two. And let's just confirm that this is shorted outside of the board. Yep. So these FETs are dead, so we have no problem in snapping these off. This next one actually read 19 ohms. It now reads 14. This next one is reading low, so let's get rid of that one. I'm gonna see if I can leave one or two in the board that have the higher resistance on them, because these FETs might be okay. We just might be reading the shorted resistance of all the others that failed. So we might be able to leave one in the board just to power it up and see if the drive circuit's okay. 27 ohms now on this one. I think there might be two FETs that survived here, guys. Oh no, okay, 34 ohms on that. And 64 ohms on that. What I'm going to do next is I'm actually going to isolate. I'm going to isolate the drive circuit, I think, from these. I just want to make sure that we're not reading a short circuit across the drive circuit here. So we have a 15 ohm gate resistor, 15 R0, and we have 49 ohms from there to there, 34, 49. That's great. Let's just remove all of them. I can always jankily solder one back in if I need to. That way we can measure it on the transistor tester as well. Matthew Macy, dude, cheers for the 10, my man. Could you name a couple of ways to quickly remove rail voltage on full bridge amps? Also, my SD12K has no noticeable damage and no short on the inputs. Strange to me, as it blew two 250 amp fuses. Does it blow the fuses straight away again when you put the fuse back in? Because obviously 250 amps, even 250 amps, 500 amps is not enough for the SD12K. The SD12K, if at a static load or at a load around 1 ohm at clipping point, will actually draw more like 1,400, 1,500 amps. So the fuse in your SD12K needs to be more like, 1,500 amps or something. FETs are normally around 800 or so. FETs don't have a resistance. What we're measuring here on the multimeter is with the multimeter on diode mode, which reads voltage drop. But the numbers that we would usually, when we're reading on the MOSFETs, we're not actually reading the FETs. The FETs have, when FETs are good and they're not damaged, they actually have a pretty infinite resistance between gate and source. So what we're doing by putting our multimeter probes on legs 1 and 3 is we're actually reading the drive circuit. Yeah, so you can see here, if I put my multimeter up here on this screen so you can see it at the top, we're actually reading the drive circuit. So with all of those bad MOSFETs out, those are the kinds of numbers that you want to be seeing on your multimeter when you read between 1 and 3 on the multimeter. You want to be seeing numbers that look more like this. This is the sort of numbers that you'll see on your typical drive circuit for voltage drop between legs 1 and 3. Yeah? It varies with amp and it varies with the circuit design, but that's the kind of values you want to see on voltage drop or diode mode on your multimeter. I have not put a fuse on it yet. How did it blow two 250 amp fuses? I'm confused by that. What do you mean? How did it blow fuses if you haven't put a fuse on it yet? Okay, so with the MOSFETs removed, let's just read these last two MOSFETs that had a higher resistance, and let's see if either of these maybe survived. I highly doubt it, but let's just see what either of these read in the transistor tester here. Okay, that one's self-test mode, so that one's definitely shorted. Just wait for it to reset. Ah, this is the only survivor. I'm a survivor. So this FET survived, and as you can see here, we can read some of the specifications of this MOSFET, which also is quite useful for helping us figure out what these FETs might be. So we have the VT, that doesn't really help us, but the gate capacitance, now that does help us a little bit. We have 5.66 nanofarads, which equates to, I think it's 5,000 PF. Of gate capacitance. So we can use that when we're looking at replacement MOSFETs for this. We can say, okay, well, the originals had around about, you know, between the 4,000 to 6,000 PF gate input capacitance value. So we don't want to go anything too crazy higher than that, and anything too much lower than that probably isn't a powerful enough FET, because the higher gate capacitance generally goes with having a more powerful MOSFET. So yes, this is the lone survivor. So I could use this one FET to put back into the board to just power the amplifier up and see the integrity of the drive circuit. Now, when you're in this situation, when you're in the position that I'm in now, where you've got an amplifier, okay, and you have diagnosed that you have one bank of output MOSFETs that failed, especially this being a full bridge amplifier. This bank over here, this side is like it's like a completely different amplifier. This is like a second amplifier. It's the same as if you're running 2 amps in strap mode. One amplifier went into protect, but the other one didn't. This is the second amplifier. So these MOSFETs, there's a high chance that they didn't really get stressed or that they're not damaged. You know, this side is perfectly fine. So although it's in the same amplifier, it doesn't necessarily mean that they are going to have any problems or be under any stress when this amplifier failed. It could have just been a drive issue perhaps on this side of the board. So we've got a few options then that we can do when we're now in this position where we've got working FETs in the board and we've removed the dead ones. Now obviously we can't power the amplifier up in its current state because we have high side MOSFETs remain in the board and low side MOSFETs out, which means that this half of the amplifier will not run properly and it will probably explode if we try and power it up. I'm just going to check that we don't have any shorts on these high side FETs. I don't think we do. These ones had rail voltage on them, so it's probably fine. Yep, this high side is okay. So yeah, I don't think that they're absolutely fine. They didn't get damaged either. So obviously you have a situation now where you can either just remove all of the output MOSFETs from the output section, and that will allow you to power the amplifier up and check the drive circuit. Alternatively, you could put a working MOSFET or a couple of working MOSFETs into the side that died, power it up to check check the drive circuit. But obviously, with MOSFETs in the board, the amplifier will try and turn on. It will try and run these MOSFETs. So that's not ideal. If there is a drive circuit fault, then that could cause more damage because it will, you know, cause the amplifier to try and run. Drive circuit fault will cause the FETs to maybe explode or maybe get run hot or something, and then that could cause more damage. So that's not ideal. What we are going to do, in fact, is we are going to isolate the output MOSFETs from the board here. So it's the same thing as removing them, but we're just going to decouple the output MOSFETs from the drive circuit. Now, there's a few different ways you can do this, depending on the amplifier. Now, if we have a look, and in terms of how quickly, how much of in a rush you are as well. So let's take a look at the amplifier here. And let's just get it sort of up a bit more so you can see. Let's get this bit of foam here, get this amplifier raised up a little bit so you can see inside. There we go. We want to go over to the output section. So these are the output MOSFETs here. I'm going to zoom in a touch more to the tiny little gate resistors. Now, in order to isolate the output MOSFETs so they don't try and switch when the drive circuit activates, one thing we can do is we can remove the gate resistors. Now, this is sometimes safe to do and sometimes not safe to do. In this instance, okay, let's take a look. What do we have here? We have a gate resistor, okay, which is coming from the drive circuit to the MOSFET gate. We have a diode, in parallel with the gate resistor, which is going to be allowing the MOSFET gate to drain its residual current after the drive has turned off. So basically the drive passes through the gate resistor on the way to the gate, and then on the way out of the gate it takes the easier path through the diode, which is cool. But what we're looking for is actually, we're looking to see whether there is any pull down resistance on the MOSFETs here between gate and source. If we remove the gate resistor to isolate this MOSFET from the drive circuit, that will prevent the MOSFET from turning on with the drive. However, if there is no pull down resistor between the gate and source, then what happens is, while the amplifier is running and powered up with high voltage on the drain here, if this gate resistor doesn't have if this gate doesn't have a small bit of a resistance pulling any residual current to ground, then electrons actually find their way onto the gate, charge builds up all by itself on the gate, eventually reaching the turn on threshold and turning the MOSFET on, instantly blowing it. So you need to absolutely, if you're going to be removing the gate resistor, you need to be absolutely sure that there is some resistance between the MOSFET gate and the source, either some resistance or a diode, which is which is getting rid of the current from the gate to the source when the gate resistor is removed. So let's just take a look. Let's see if there is any resistance between these two. I'm going to want to go up to ohms mode now. Let's go. So we're on 200 kilo ohms here. Okay, there doesn't seem to be any resistance there. So we don't have a pull down resistor, which probably means that the thing that's preventing excess charge building up on these gates is going to be integrated into this little drive chip. So these are the final drive buffers, which are actually driving the MOSFETs directly. And inside these chips, there could be a diode across the gate path and the drain, and the source, which is preventing excess current building up on the gate. So let's just see. We have continuity then between the MOSFET gate, which is just over here. We have continuity between MOSFET gate and the driver here. Let's see which driver it is. One of these ones. Helps if I have it on the right setting. Okay, so here we go. This driver here, which is currently hiding behind this capacitor, this driver here is what has continuity to our high side FETs on the bank that blew the low side. So do we also have continuity to anything else? Here we go, D27. See this diode here? This also has continuity to the gate. Now, if this also has continuity to the source, we may be in luck. Oh, it does. Okay. However, the orientation of this diode suggests that the diode is blocking current from the gate going to source, which is not ideal. That's not going to help us here. Okay, so in this instance, I don't feel particularly comfortable solely removing the gate resistors from these MOSFETs, because I cannot guarantee that the MOSFETs won't randomly power up by themselves with the gate resistors removed. So now, in that case, then the next best thing to do is to isolate, to remove connection between the drive chip and the final drive buffers. Now we can very easily do that by removing these 100 ohm resistors here and here. So this chip, the driver IC, has its PWM output. It goes through these 100 ohm resistors and then into these final drive buffers. So by removing these 100 ohm resistors, we prevent drive getting to the FETs, but while still having the MOSFETs connected to the drive architecture, the drive chip here, which is going to be controlling them and preventing them from randomly turning on. So let's turn on our hot air station and let's remove some of these resistors and get the amplifier powered up so we can check the drive circuit. Damien has a good idea actually. Can you put in single resistors per bank? Yes, you can. But obviously for every gate resistor you remove, that MOSFET leg, that gate leg, now doesn't have any connection to the trace going back to the drive circuit. So you'd have to solder a resistor on every single MOSFET, like a 10k resistor. You could even just use a jumper. You could just short gate to source, and that would prevent the MOSFET ever turning on. But you would have to create a jumper or a resistor between gate and source for every single MOSFET that you remove the gate resistor for. So let's get rid of these 10 ohms on both sides of the amplifier. You know what, actually, we could probably leave the ones for the other side in. Where's my flux? ¿Dónde está mi flux? Asking to see it. Oh, here it is, on the table. Ah, pizza! Pizza sounds great. Just going to preheat the area a little bit first by drawing some circles around it. If you don't preheat the area first and it's stone cold Sauvignon, then what tends to happen is you can actually bubble, you can popcorn the board, which is not ideal. So we're going to put these 10 ohm resistors safely to one side. You know, I've got hundreds of 10 ohm resistors, but might as well keep them safe, seeing as they're fine. There we go. That's those two removed from that bank. Now let's do the bank above. Ten ohm there. 10 ohm there. Okay. Okay, so that's all that is that's just 4 resistors removed. And by removing those 4 resistors, we decouple the output drive IC to the drive buffers, which prevents the MOSFETs from turning on when the drive activates on the amplifier. And like I say, the reason we've done that is because we want to check the integrity of the drive circuit. We want to check to see whether the drive circuit is okay, see if it survived, especially this chip here. This chip is the part of the bank where the low side died. So we want to make sure that we get drive on the output of this chip here. So now we're ready to power the amplifier up and see if we get drive on the output of the chip. So we're going to take our oscilloscope probe. We want to be probing those resistor pads that we just removed the 10 ohm resistor from. So over here, C5. So you see the empty resistor pads. We have this one here and this one here. So this is going to be high input or high side or low side output. They got high and low, one of each. So yeah, let's get the power supply turned on. We want to go for a nice low voltage. We don't want 12 volts. Let's go down to about 10.2. I think that's going to be high enough to get the amplifier powered up. Now there's going to be a scary high voltage in here actually. This amplifier is going to be scarily high voltage. This is a 16k or 20. There's going to be a lot of voltage in here. So yeah, definitely don't want to be making any mistakes with that much voltage on tap here. Let's give a 5-6 amps. This is a pretty big amplifier. I know we're not switching the output section, but let's give it 6 amps. and see how we go. I'm going to take one oscilloscope probe and I'm going to turn channel 2 on the scope on. And we're going to put the probe for channel 2 onto the rail, just so we can monitor what the rail voltage is doing, because we just want to see, you know, it go up and stuff. Let's have a look. We have... So as we pulse the remote, I'm pulsing the remote now, we can see the rail voltage here is rising slowly but surely. We're now at 37 volts. Still rising, still rising, still rising. So what I'm having to do, I'm having to pulse the remote like do, because this amplifier is detecting that there's not enough current available to turn on, you know. So that's part of the health check mode, is to check that the amplifier is being fed with enough current to power up. Obviously I'm limiting it to 6 amps, which is not enough current. So by pulsing the remote like this, every time we pulse the remote we build a little bit of rail voltage, until finally we get to the point where the amplifier is like, ah, yeah, cool, no worries, that's enough rail voltage, let's go full power, let's turn on fully. Just pulse, 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 get it high enough, and at some point you'll see this will start to quickly rise up. Shit, we got it. So we got 100 volts already on the rail. 100 volts DC on the rail already. Now, with 100 volts on the rail already, what I'm going to do is, before I power the amp up fully, I'm just going to check and see if there's any differences in the voltages that we see on the... Fortunately, we have obviously a drive circuit here which is fine, which survived, because this half of the amplifier is fine. So with a full bridge amplifier, if only one side died, the other half of the bridge is a perfect working example for you to take notes from. So in this instance, we have a perfect working example on this side that we can take some notes from. So let's take a look. On the output of this one, closest to the point, we have how much volts? We have 43 volts, which is pretty much exactly half rail. See that? 43 volts, which is what the amplifier is treating as 0. So that's going to be the high side gate. And the low side gate is going to be the one down at 0 volts, which is down here, this one. This one's going to be the low side. So yeah, we have 0 volts on low side gate, and we have 42 volts on high side gate. So let's just check that that's the same over here. 42 volts on high side gate and 0 volts on low side gate. Okay, good stuff. Let's also just check what we have on the MOSFET pads over here to make sure that that's the same. So this high side, we have, on this one, we have half rail, positive rail, half rail, and on the low side we have 0 volts, half rail, 0 volts. That looks good to me. That looks good to me. So let's continue turning the amplifier on while we're probing this. We're going to probe the low side PWM output from the chip, which is this one, and let's see what we get. Right, now the amplifier is coming on fully. See that when I hold the remote down now, the voltage climbs continuously. So let's turn the voltage on the power supply down a little bit. 10.1. Okay, here we go. Now it's going to come on. So the rail voltage with 10 volts is sitting at 155 volts-ish. Okay, so if we take a look at what we have on the oscilloscope screen, you can see there that we don't have any low side drive coming out of that. On the other one, on the high side, we don't have any drive either. And on the good bank that survived, we don't have any drive either. So we don't have any drive anywhere on any of these pads. Now, next thing that I want to do is I want to apply some signal. Let's get the RCA wire. Let's give it 40 Hertz and see whether that kickstarts any drive into the amplifier. Just going to turn the gain down, high pass, low pass down, gain is at minimum already. Bass boost, the bass boost was fucking maxed out on this. Actually, you know what? All of the knobs were maxed out other than the gain. on this amplifier, the high pass was pretty much almost maxed out. The low pass was up really high. Gain was at 0, but the bass boost level was maxed out, and the bass boost frequency was up really high as well. What? Why? That doesn't make any sense. That's the very nonsensical selection of settings there, sir. Okay, so now we have, let's give this 47 hertz going into the amplifier now. So let's power it back up and see if we get a 47 hertz PWM on the output of that drive IC. No, we do not. We still get absolutely nothing. Okay. And if we take a look at the side of the amplifier, the lights that are lit on the amplifier are power and clip. Now I believe that I think the amplifier believes that it's clipping or something, and it could be a signal issue. Now usually when I see sound digital boards that give this kind of problem where you have no drive whatsoever coming out of the drive ICs, even though the amplifier is powered up and should be trying to operate, a lot of the time the reason for that is because the failure of the MOSFETs has actually killed part of the circuit that is responsible for generating VCC for these drive ICs. So these drive ICs, these need obviously power to work. Not only do these need power to work, but all the other op amps in this drive circuit also need power to work. So what we just want to do is we want to look up the data sheet for this output driver, and we want to check which pin is its power input, its VCC. We want to make sure that we actually do have voltage going to those pins, and if we don't, then we can trace back to the circuits which generate those VCC voltages. Now fortunately, because I know a bit about these amplifiers, I've repaired these before, I already know where the circuits are that generate different VCC voltages for this amplifier to come to life. So over here we have a little pulse generator, and this is responsible for generating this is responsible for generating the VCC voltage that the power supply driver uses. For example, that's one of the chips that uses this VCC. Now we know that that's working because it's running the power supply FETs just fine. Power supply FETs come on, amplifier comes on, builds rail voltage. So this area is fine. There's another voltage generator circuit up here. Over here we have a pulse generator, which is just this tiny little chip up here, the same circuit as down here. We have a pulse generator, we have a couple of diodes, big rectifiers, we have an inductor, a couple of capacitors, and this will be generating VCC voltage. Now what we want to make sure is that this pulse generator is working. And for this pulse generator to work, we need to have 5 volts on the input of this pulse generation chip. So let's have a look and see on the scope screen, what do we have when the amplifier comes on. There we go, we've got 5 volts. So, okay, that's cool. This pulse generator should be generating pulses. So let's have a look on the output of it, and let's make sure that it is generating some pulses. Yep, there we go. There's some pulses. Okay, so that's working, so that's creating VCC. So that is probably going to be sending VCC voltage to the right places. Yep, okay. That generates 15.9. There you go, see that? So that little circuit there generates 15.9 volts for some of these chips to work on. Let's have a look and just see whether we have any of those voltages around here. Okay, 16 volts. Yep, so that generated voltage is getting to the drive buffers. That's cool. So I think the next thing that we need to do then is bring up the data sheet of these drive chips, and let's find out what their pins are, and then we can see what voltage is on each of the pins, and and see where the problem is. Mike Connor says, Bevis, I wonder how did the QC power sticker get inside there? Especially if you're repairing it and it's new. The QC... Oh, no, this sticker, this obviously would have been done at factory. So the board will be assembled, you know, the board will be built and have the parts soldered in. And then it will be assembled into the heatsink. And then this amplifier will be tested for quality control before the back is put on and before the warranty sticker is put on. So that's how that sticker got there. Okay, yeah, so let's remind ourselves then, what chips are these that this uses in the output section for the output drivers? Now, off the top of my head, I can't remember, but I did make a YouTube video about what they are. So let's go onto YouTube. Actually, I don't even need to do it. I think I can just check. I can just check an amplifier that I've got here because I've got a Sound Digital 8K which uses the same drive circuit. let's grab this Sound Digital 8K right here off the back burner. Okay, this is using IRS 20957s. Okay, let's just check that's the same circuit. So here we go, that's the circuit in the B2. And this is the circuit in the Sound Digital. Yep, it's the same. Exactly the same circuit. Just slightly different output drive buffers, but it's the same circuit. So yeah, provided this has the same number of legs and has the same voltages and whatever and the same pins. 1, 2, 3, 4, 5, 6, 7, 8. So we have a 16 leg drive chip. It's probably going to be the same one. 1, 2, 3, 4, 5, 6, 7, 8. Yep, it's the same. So it's an IRS 20957S. So let's grab the data sheet for that on the interwebs. Okay, so as you can see, the topology of this is a half-bridge drive chip, which means that this amplifier is essentially 2 half-bridge amplifiers on one PCB. Yeah, it's 2 half-bridges on one board. Now, the pinout. Where is the pinout for this? I saw it at the top there, but I was hoping there was a bigger version of it somewhere. There we go. There's the big version. So, floating input positive supply, VDD, low side logic supply, there we go. That's one of the things that's important. We need to have low side logic supply. This is going to be the supply voltage that's going to be getting the drive through this chip. And we also want to see where the input is. So in PWM non-inverting input, in phase with high output. So we need to have some PWM on pin 3 in order for this chip to be outputting some PWM. We also need to have VCC on pin 11, and we also need to have, I think, VDD. That varies depending on the floating input positive supply. Yeah, so let's have a look then. So first of all, let's check pin 11, low side logic supply. See what we have on low side logic supply. Pin 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This one right here. Okay, low side logic supply has 15 or 16 volts on it, which is correct. That's what we'd expect to see. So I'm happy with that. So the chip is getting power. That's fine. Next then, on pin number 3, we need some kind of PWM going into pin number 3. So let's have a look. At pin number 3, we've got RCA signal going into the board. So usually with these, you get some PWM going into pin number 3 based on your signal you're feeding into the RCAs. Let's have a look. Pin number 3, give you the scope screen. Aha! Yes, we do. Look at that. We have some signal going in. Okay, so what if we've got signal going in? Why don't we have signal coming out? How strange. Okay, let's check the other pins then. So we've got signal going in. Now, is there a shutdown pin or something? Let's have a look. Shutdown timing capacitor, reference to VSS. Okay, so shutdown timing capacitor. This is going to be referenced to pin number 4. Pin number 4 is floating input supply return. So, it doesn't actually tell me on this whether CSD should be high or low to shut down this chip. But let's have a look at pins 2 and 4 then. Because pins 2 and 4, depending on what voltages are on there, will tell us whether this chip is in shutdown mode or not. So pin number 4, let's read pin number 4 first, which is VSS. Pin number 4 is ground. Pin number 4 is 0 volts, or like negative rail pretty much. So pin number 2, what do we have on pin number 2? We have 6 volts, okay. So I'm not sure, I'll have to look at the datasheet a bit more, whether CSD should be high or low. Here we go, it goes low. So it starts off high, and then it goes down to what looks like 4 volts. Okay, so when the amplifier is first powered up, it's at 5.8, and then it goes down to about 4 volts. So that seems to suggest to me that high is shutdown mode, and then when it goes down low, it should activate the chip. But it's not. It's not going all the way down low, is it? It's going just down a little bit. It's going from 5.6 or 5.8 down to about 4 volts. Check pin 1. Nearish says check pin 1, see if you're getting 5 volts on that pin. Pin number 1 is floating, VDD, yeah, floating input positive supply. Let's see whether we have that. Although I don't think that won't affect our low side drive. We should still have low side drive output even if we don't have 5 volts on pin 1. But let's just check anyway. Pin number 1. Let's see. Do we get the 5 volts? We get 10 volts. So yeah, that means that it's using 10 volts to drive the high side, I imagine. I think, yeah, that's probably what that is. Okay, so we seem to have all of the right voltages on the drive IC, apart from maybe the shutdown. That doesn't seem right to me. So let's have a little look at the datasheet and see if it tells us anything about CSD, whether it should be high or low. CSD to shut down waveform definitions. That's a little graph there. Can I zoom in a bit more? Can you give me? Here we go. Zoom in. High, low. No, that's not quite what we're looking for. Zoom out again. Let's go next. I just want to know. Should CSD, should the shutdown pin be high or low for activation? Here we go. So this is the circuit for CSD referenced to VSS. There should be a capacitor in that circuit somewhere, no? Or is that the internal diagram? CST, discharge, protection control. That doesn't tell us whether it should be high or low either. But I think it should be low. Yeah, it must be low. It must be low. Shutdown program delay from VCSD to VSS. Here we go. Time shutdown. Yes, CSD must be low for operation to begin. So what this here is, this is time for shutdown, I think. So shutdown propagation delay. So the amount of time delay which there is from voltage CSD going to voltage VSS plus V, whatever the fuck this one is, to shut down. So, or maybe shutdown's low then. Oh, fuck, I don't know. Guys, what you got? You got any ideas in the chat? Does anyone know, should CSD be high or low? I could probably find out, because actually I could probably just power up. Oh, I say that, but I think I stole the power supply chip for this. I could probably try and power up this sound digital board here and see. Although I might have another sound digital board. Yeah, I do. I've got a sound digital 12K that I could take reference from. So if none of you guys have got just any suggestions, I'm just going to double check with a working amplifier to see whether CSD should go high or low when the amplifier turns on. Dean says it's a shutdown. Yeah, I'm aware that the volume of the video changes when I change cameras. I can't figure out why. Honestly, we've been through this before on this live chat, and I don't understand why the volume changes. It's very frustrating. I've tried to figure out why it does it, but I no matter what I do, can't figure it out. There's no filters anywhere on any of these. Advanced audio properties. I think what I'm going to do is I'm going to grab the working Sound Digital 12K, I think, and just have a look and see what it should be. I think there is one just down here somewhere. Here we go. So this is a Sound Digital, well, it's actually Ground Zero branded, but it's, yeah, it's the same board basically. Same board. This is the Ground Zero branded version of the exact same circuit, literally down to a T, the exact same circuit. So this amplifier works, it just needs a new output, and just needs a couple of new power supply MOSFETs, but it has enough in it for it to come on and function. So let's have a look then at this one. Let's see, what is the CSD voltage of the one that works? Okay, power is into this board now. So let's get this one fired up. And CSD was pin number, what was it? CSD was pin number 2. All right, pin 2. So we're looking at pin 2 on this when this fires up. Okay, so we have output switching on this amplifier. So now let's go and have a look at pin 2 then. Let's see what it does on this board that works. Pin 2. Let's get that probed in there. So we start off with the same value. We start off at about 5.7. And then when the amplifier comes to life... Oh, it actually goes up. It goes to 9. Rare. Okay. So his shutdown is low voltage and it needs to go up to about 9 volts then when the amplifier is activated. Interesting. Okay, that is very curious. Now you might think that might have something to do with the output MOSFETs being in the board in this one. This amplifier is fully functional. It comes to life. All the FETs are fitted. It produces audio, etc. I might be curious to find out, just to check, on this Ground Zero board, remove the same 4 resistors that we removed on this B2, and see how the CSD, see how it behaves with the output MOSFETs disconnected from the board. So I think that's probably what we're going to do next then, guys, just real quick. Let us quickly remove the resistors on the Ground Zero branded Sound Digital board and see how the CSD behaves with the resistors out on this one. Bring the rail voltage down to ground real quick on here. Let's ground and rail voltage. There we go. Nice big spark through the 16 ohms of my pull down resistors. Let's get the hot air gun. Let's remove the 4 same resistors in the drive circuit that we removed on the B2. And that's the resistors that are responsible for isolating the drive ICs here and the final drive buffers. One, two, three, and 4 resistors removed. Okay. So this amplifier now has the output FETs isolated, the output drive isolated from the drivers. So let's power it up again, and let's see what we have. How this, I want to see how the CSD pin on pin 2 behaves with no output MOSFETs. You know, with the MOSFETs decoupled from the drive circuit. And I also want to see what kind of drive we get on the outputs of the drive chips with no MOSFETs coupled to the board. So let's power it up again, get the scope screen, and let's first of all let's look at what pin number 2 does. Let's get the rail voltage built up. There we go. Okay, and probe pin number 2. Okay, it bumps up. Yeah, okay, so it doesn't go quite to 9 volts. So with the the MOSFET buffer drivers decoupled from the drive IC, the pin 2, the CSD, it behaves as such. It starts off at 5.5 volts. Then we have a little glitch. Oh, actually, the amplifier goes into protection, actually. Why does the amplifier go into protection? The amplifier should stay on. No? Why is the amplifier going into protection? Hang on a minute. Shouldn't be happening. It should stay on. Well, that's really annoying. Now the amplifier won't stay on. But I think we've decided that CSD needs to go up anyway. I think CSD needs to go up to 9 volts. Why aren't you staying on? Flashing the clip LED at me. That's very unusual. Usually, you can perfectly fine power these amps up with the drivers decoupled from the output buffers, and it just powers up fine. I'm not sure why the amplifier is going into protection by flashing the clip LED at me. Very strange. I've not had that occur before. But okay, perhaps then, since I last looked at these, maybe the health check mode has been updated to go into, you know, protection, whatever, when it detects that no switching has started. So alright then, okay. In that case, with our B2, perhaps the correct thing to do then is actually to fit the one remaining surviving MOSFET to that bank, recouple all the drive circuit, and just see what it does, you know, how it behaves then. I think that might be the thing to do. Mike Connor said, I remember an amp you repaired before. I had a similar issue, we just needed the components replaced in order to complete the health check mode. Yeah, I have done a couple like that, but these Brazilian ones, I've definitely shown before. Like, so in the video that I made about these sound digital amplifiers, which are all the same kind of thing, I definitely was able to power it up and show you the drive waves with the output section decoupled like this. Let's have a quick look, see what I did.
Here, which is exactly the same. In my case,
now do I get the scope out and show waves? Here we go.
by the way, already rises up with. Okay, should be.
Here we go.
Have a messy looking wave. It's a very, very.
That's the voltage regulator. That's the voltage regulation section.
We have about
with the output drive.
WM waves on those resistor pads or on the legs of the drive IC itself, mimicking what you're putting in from your signal generator. If you're repairing one of these and you are removing the drive ICs anyway, just to understand these boards a bit better, it's a good idea while the drive ICs are removed to actually start to power the amplifier up on a very, very low current.
Yeah, I don't think I actually show it because I think this was a working example. Okay, cool. Let's put the resistors back in. Place a surviving FET in the this board here, and just see what happens. Like this is the dangerous solution. This is the solution where it could just kill a bunch more stuff. But I think that's the thing that we need to do right now. So let's just get rid of that rail voltage. We still have 59 volts there sitting on the rails. So let's get that grounded. See, that went down to ground nice and quickly there. Let's put our 10 ohm resistors back in the board then. Okay, so now we have the drive ICs recoupled with the final buffer chips, and the last thing we need to do is we need to fit a FET into this bank that blew before. Doesn't matter which one, doesn't matter which pad we put it in. This ground trace has such a high thermal mass, and as you will know, my soldering iron is out of action, so I'm having to use hot air for everything temporarily tonight. Yeah, this has ridiculously high thermal mass, this ground trace, Jesus. Wow. That's quite something, that is. New tips for my iron should be arriving, what day is it today? Monday. Yeah, it should be arriving this week. I suspect they'll either arrive tomorrow or Wednesday. This is going to be a pain to try and solder this with hot air. Ah, man. There we go. So gate and drain are soldered. I just need to solder this source leg, which has insanely high thermal mass to the board here. Very, very high thermal mass to the board here. Oh, there we go. We've soldered it good enough for it to be making electrical connection. It's not very solid, but it will do just for powering the amp up sakes. Okay, so yeah, this is the point where it's either maybe gonna... So there's a few things that will happen here. Either the amplifier will start switching and work, which is great, which means the drive circuit survived. Either the amplifier will try and turn on and go straight into protection as soon as switching starts to activate, or the amplifier will explode, will kill the output MOSFET that we've just placed in the board. So let's see which one of those happens, shall we? Switching should occur on the low side drain, which is this leg here. So let's see on our scope screen what we have when high voltage starts going into this board. Now I'm going to protect myself with some safety goggles here, because when these MOSFETs explode, the such high voltage will send shards flying through the air, which isn't ideal for anyone. All right. So amplifier's coming on. As you can see on the scope screen, the rail is building. Okay, guys, here we go. Now it's about to come on. Whew! Scary bit. Scary bit. Okay, it does actually come to life. What the fuck? Weird. Okay, so they must have actually changed the way that the health checks mode works in this amplifier then. Yep, the amplifier comes on. Okay, so that tells us the drive circuit survived. Great. Awesome. So we spent a little while faffing around with that drive circuit for nothing, but that is very strange. So I have now update my mental notes, and you should do the same then. So these new amplifiers coming out of China that are based on Sound Digital boards, there doesn't seem to be a way for you to check the drive at the MOSFET gates without the MOSFETs being there yet, without some tweaks. There will be some tweaks that you can do where you jump some voltages around on the drivers to get them into forced activation. I imagine that the voltage on the shutdown pin needs to be locked at 5 volts or something in order for it to to pass that PWM to the output. So because we did used to be able to do that with the older standard digital boards, we did used to be able to do that with the MOSFETs out and with the drivers decoupled. So yeah, very, very interesting that we can't do that now. But that's something to bear in mind then, that we can't do at the moment without some further investigation as to what to put onto, you know, those what sort of jumpers to put around the drive circuit to force it to oscillate without the MOSFETs in. But I wonder then, so why did those 6 MOSFETs die? So this amplifier come in with 6 dead output FETs along here. Now why did they die? With the drive circuit, it seems to be fine. So it doesn't seem to be the drive circuit that killed the FETs. I wonder whether there's like an inductor short. I could possibly like power the amplifier up and like wiggle the inductor around and see whether it you know, does any strange stuff with this MOSFET. Maybe we could try doing that. Probably want to get a piece of fabric though, because if there is any of the laminate that's come off of that inductor, if I touch that, that won't be too good news, because that will, you know, that's got pretty high voltage on it, because it's sinking, it's filtering high voltage stuff. So I'll put that on there like that, that'll be alright. No, that seems okay. I mean, like giving this a wobble doesn't seem to affect the drive on the output there. Yeah, that seems okay. So it doesn't seem to be like an obvious inductor short. So yeah, very interesting one. Seems that we just had dead output FETs with no real explanation as to why. And this is a relatively new amplifier as well. So could just be that it was overloaded slightly. But a few other people said that they experienced a similar thing with this. Bad batch, it's common. 3 out of 10 amps don't make it out of the factory. Yeah, Tron, that is also a very plausible suggestion. These MOSFETs, they are such high current and such high, such low RDS, and they're so hard to drive, and you know they're very, very modern and cutting edge MOSFETs. That is very possible that just one of these FETs just wasn't happy, was slightly different tolerance to the rest of them, and didn't like being run in parallel with the others. Yeah, very possible. But yeah, so this amplifier will work absolutely fine now. I didn't need to do anything to the drive circuit. So hopefully this has been a somewhat educational stream about these new B2 Riot 16K amplifiers, what their circuit design is like. If you missed that, go back to the start of the video and watch me talk through this circuit and explain to you the differences between this and other amplifiers, how it works, and the choices, the design choices that have been made here. So go back and look at that. Also hopefully if you are looking at repairing these at any time, hopefully that my little investigation there with the drive circuit has helped you in future with diagnosing the drive circuit, in that you don't expect to get any drive waves without the MOSFETs in, or with the drive buffers decoupled. You won't get any of that. So that is also important to know for when you're diagnosing these. And what I'll do, guys, I have a Discord server now where I'll be posting smaller updates with this kind of stuff. So when I'm obviously this amplifier just needs new FETs, but I will be doing some investigation with this amplifier circuit design, and I'll be looking at a way to force the output drive circuit to provide PWM switching all the way to the output drive buffer chips without needing the MOSFETs in, or without having the MOSFET drive buffers coupled to the drive circuit. I'll make some changes, some jumpers, some resistors and stuff, and I will I'll post those updates in my Discord server under what I'm working on. I think I've got a Discord server thing called what I'm working on currently. So if you want an invite link to the Discord server, I'm just going to get that now. Bear with me a sec. I shall grab the invite link to the Discord server. How am I not logged in on this PC already? There we go. Oh, no. Email or phone number. Okay. One sec. Here we go. Here's the beverage. And I need to go up to here. Share channel. How do I share it? Server boost, invite, server settings, create, notification, privacy. How do I get a link? How do I get the sharing link? Maybe I just copy the URL. Try this. Try this link. See if this link works. Does the direction of the resistors matter? No, it doesn't. The direction of the resistors does not matter. Because they're non-polarized. Create an invite link with unlimited time. Alright, how do I do that? Notification, privacy, server settings. Invite people. Here we go. The invite link expires in 1 day. Here we go. Edit invite link. Expires after. Never. Set maximum number of users. No limit. Grant temporary membership. No. Generate a new link. Here we go. Copy. And here we go. There is your infinite invite link. And I shall also update that one on my beverage page so that you can see that one on the page as well. Beverage, I have 2 door enclosures, 2 drivers per enclosure. I have tiers parameters for each driver. What would be the best parameter to pair them by? So the drivers are not the same then? They're different? Snipex says, well, anyway, how is the DSLR camera thingy going? Is it any good? I didn't get a chance to install it before my live stream this evening. Literally, I was like running down to the workshop at like 5 to 10 and opened it up because I was really busy today during the day. So I haven't tried the DSLR thing, but in the future streams, maybe tomorrow, maybe sometime next week, I'm going to try hooking up my DSLR camera as an additional camera angle for you. I just need to work out actually what would be the best angle for my DSLR camera. So obviously we've got the big camera up here. Now this is a JVC, like old sort of handheld camera that's zoomed in real far. These are great for that actually. They zoom in. The optical zoom is phenomenal on these. And so you get a really clear image zoomed in, but obviously the rest of my cameras, like this is a Logitech webcam from like 2010 or something. This here is a Logitech webcam with a low frame rate from 2010. The camera for my scope again is a cheapy Logitech webcam, but they all work okay. You know, not necessarily the clearest picture. So maybe I could give you my DSLR here at my face. Not that that really matters. You don't need to see my face in any considerable clarity. So I could change this one for the DSLR, but this one does kind of work okay. I could add a second camera. So the one camera that I don't really have, I have this camera which I use for zooming in on stuff. I have this camera which I can move around, but I don't have a camera that is always like just an overview of the board, the whole board from a bird's eye view. So maybe I could somehow set up my DSLR with a decent lens that's a good high sharpness and clarity to give you like a top down, or maybe just from behind my shoulder. Maybe I'll hook up a camera behind me like I used to, looking over my shoulder maybe. What kind of camera angle would you like to see used with the DSLR camera? They're all the same drivers, but the TS vary a little according to DATs. Oh, okay. So which one would you match them on? I would match them on... Well, sorry, if they're the same driver, yeah, if they're the same driver, then they're going to be assembled the same. They're going to have like the same motor and the same gap size and stuff like that. So the only variance between them is going to be FS, and the varying FS will vary all the other parameters because they're all linked. So I would match them on FS. what you're doing now works just fine. People say probably from the top, SnipeX. You should probably try all angles on the stream so we can decide. Yeah, could do. It might take a little while though. Top view, your shoulder. Yeah, I'll probably, yeah, I'm going to go for like above somehow. Quite high above, maybe over my shoulder. I'll try and get like a big, tall camera tripod in here or some way of getting the camera up high to give you that view. Yeah. Yeah, okay. I'm also moving soon. I have an offer accepted on a new house. So I'm going to be moving. So basically, there's going to be a new workshop. So in the new workshop, I'm going to be, building and accommodating for all these different camera mounts and attachments and stuff like that. So yeah, I will be redoing everything in the new workshop at the new place. So I'll be able to buy like wall mounts, adjustable brackets and stuff to give you the best camera angles. Could you show the pedal that you use to change screens with? Yeah, it's literally just the cheapest USB pedal from like eBay or something. There, here we go. That's the pedal set I use to change cameras with. Yeah, pretty cool little thing. I did originally plan to get 2 of these and have 6 pedals, so I could cycle between. Because obviously I've only got 3 pedals there, so I can only the pedals only cycle between this camera as pedal 1, this camera as pedal 2, and this camera as pedal 3. For the scope cam, I actually have a little Akai LPD8, which is like a little kind of drum pad here that I have some assigned some buttons to. So this one is for the scope screen, and this one here is for the screen capture. Yeah, this one's for the scope, this one's for screen capture. I also have some sound effects mapped as well, which I don't use very often because I keep forgetting that I've got them. So yeah, this is a pretty cool little thing that I can play with while I'm streaming. Would like to see what amplifier drive waves operate without affecting the board. Yeah, for sure. So I'll work on that with this amplifier and see if I can make some modifications to allow the drive waves to be there without affecting, because this amplifier doesn't seem to like that. Ah, thanks Bevis, bring back the hat cam. Yeah, so for a while, a couple of years ago when I was live streaming, I strapped one of the webcams to my head on my hat, so I was able to like put my hat on and have a camera like a bird's eye view so you can see what I see. That was actually a really good camera view. I think that's a great idea. It's 13 BTRX3. I will bring that view back. I'll get another hat and I'll strap a camera to my hat like I used to, because that was a pretty good camera view. It was a little bit shaky, but it did work really well actually. That was a pretty cool view. What happened to the chick you had with work on the amps with the hat cam on? That's my good friend, Ashley. Yeah, she's alright. She's doing alright. She's moved quite far away actually now. Our friend group doesn't get to see a great deal of her. Yeah, I think she's doing okay. Soldering iron cam. I did also have a soldering iron cam. However, the problem with the soldering iron cam was that firstly it made the soldering iron a bit of a bitch to use. Obviously, I had this big freaking camera off it. I could buy actually from AliExpress or Banggood. I could buy a very, very small, like a spy cam that didn't, make the soldering iron bulky. That would be a really great camera to have. And I'd have to like glue it or strap it with something to the soldering iron, because before I just used duct tape, because I was just like quickly duct taping it to the soldering iron to see if it was a good idea. And naturally, the soldering iron gets hot and the handle gets hot, and so the duct tape melted. So yeah, maybe I'll get myself a nice high quality like small miniature camera that I can attach to my soldering iron and give you soldering iron view. That did look really cool actually when I did that a few years ago on the streams. Okay, cool. Yeah, so guys, I think I'm going to lock the stream off here. Thanks for joining. Hopefully it's been educational as always. And I hope that you know a little bit more about these amplifiers that are based on Brazilian designs that are coming out of China now from various brands like Ground Zero, B2, etc. So yeah, thank you once again for joining me. And yeah, we'll catch you very, very soon in tomorrow's live stream, because we're streaming every single night in December up until Christmas Eve. So if you're not doing anything in the evenings, if this kind of time suits you, then jump on and join me while we investigate, diagnose, and possibly, hopefully, repair some amplifiers. Cool? Take it easy, guys. I'll see you tomorrow.